Okay, we're going to finish up focus 8. So we're going to talk about both topic C and D. And as we look at topic C, okay, as we look at topic C, what you're going to notice is that there's really no new insight given in this compared to a Gen Chem text. These are kind of complex issues. So they give you the same kind of description of why atomic radii, why ionization energy, why electron affinity have the trends that they do. So read through this section. And I think the only thing that I will point out is there are discussions comparing delta U to delta H. Given we're doing things out of order, that's something that you would be familiar with from doing the thermodynamics sections, and we haven't done that yet, so don't worry too much about being able to distinguish a delta U from a delta H. It's really the only thing that they add in this. But other than that, just read it through. There are only a couple problems in the your problem set from this, and they're pretty straightforward. They're pretty much Gen Chem level understanding. So we'll move then right on to something that is pretty new, and it's the idea of spectroscopy. So we're talking about atomic spectroscopy. So looking at individual atoms, not molecules. And when you have individual atoms, they can't rotate, they can't vibrate. So the only kind of energy, or the only place you can put energy, is into the energy of the electron. So when we look at it, we've already learned about the Bohr frequency principle, which says that anytime light is absorbed or emitted, the photon of light has to be equal to the energy difference between the two states that resulted in that photon. So this is a way to understand better the energies of orbitals. And so like we discussed in topic 8b, where we said that if you use self-consistent field calculations, you can get really good agreement with experiment. And so this is what you'd be talking about. What are the actual energies that an electron can take on, and you can measure those with spectroscopy. You can't measure all of them because it turns out that there are things called selection rules, and a selection rule is just a statement about which transitions are allowed. The primary reason for selection rules is that, I didn't bring a pen, oh, there's one. Nope. Is that a photon is a spin 1 particle, so it can carry away 1 unit of angular momentum. And so when we look at the selection rules for atoms, that means that you can have transitions where L, so up here in the left-hand corner, change in the L quantum number has to be plus or minus 1. That's equivalent to the angular momentum of the photon. So if a photon takes angular momentum away, the system has to change by the same amount because angular momentum is a conserved property. So this selection rule for hydrogen-like atoms is pretty simple. It just has to be a state change where delta L changes by 1, or yeah, plus or minus 1, and then delta M, so the projection of that can also change by 0 or plus or minus 1. So this picture at the bottom is just a visual way to show that. So for a hydrogen atom, the N equals 1 state, N equals 2 state has S's and P's of equal energy. So you could have a 2p electron going down to a 1s electron, and it doesn't matter the 2 and the 1. All that matters is that the L quantum number changed from a P to an S, so it changed from a 1 to a 0. So that's allowed by the selection rules. So this brief illustration just helps you think about it, and then the self-test. To what orbitals may a 4s electron make spectroscopic transitions? So it can go to any n level. N doesn't involve a change in angular momentum, but it has to change by its L value by a factor of 1. So there's nothing below 0. So the only orbitals that you could go to are any n value, but they have to be p orbitals. So that's for the hydrogen atom. Now when we look at many electron atoms, things are going to get more complex, and we are going to think about the energies, and we're going to call them terms. So a term is the states the electron would start in, and then the state that the electron would finish in. I'm just going to keep going, even though the phone's ringing. That's okay. So we're going to talk about, in many electron atoms, the electrons can interact with each other, and they can interact in two different ways. Their orbital angular momentum can interact, and their spin angular momentum can interact. So if you think about it, you have orbital angular momentum of one electron, and it can either be aligned with or against, or some combination of that with the other electron. So we have what are called Clebsch-Gordan series in order to think about how they could align. So at the bottom here, this equation is going to be an important one. The overall orbital angular momentum is given a capital L, and it can either be anything from the two electrons' orbital angular momentums are aligned in the same direction, and so they add together, all the way down to the place where they could be aligned anti, and then depending on their magnitudes, the absolute value of that will be the sum of those two vectors. So the bottom on page 382 just shows you in a vector sense how those can be added. So you could add two electrons that are both in p orbitals, so L1 equals 1 and L2 equals 1, so the L quantum number. And they could add in such a way to make a longer vector where you have them aligned, and then large L, the angular momentum of those two electrons together equals 2. Or they could be aligned in such a way to have L equals 1, so that's where they're not aligned together and they're not aligned exactly opposite, they're somewhere in between. And then you have the other extreme where L1, so one electron's angular momentum is aligned in one way, the other one is exactly opposite, and so they add up to 0. So that's just a visualization at the bottom showing you what we're talking about when we're thinking about this. So this first self-test says just identify the terms that arise from an excited state of calcium. So the only electrons we have to worry about are the unpaired ones. So we have two electrons each in d orbitals. And so L1 equals 2, L2 equals 2. And so if we want to figure out what terms we have, L can be L1 plus L2, all the way down to L1 minus L2 absolute value. So that would mean it can be 4, 3, 2, 1, and 0. 2 minus 2 is 0. So we're going to have terms that we'll call an S, a P, a D, an F, and then remember, once you go beyond what we have in the periodic table, then you just start using the alphabet. So those are the terms that we would have. We'd have G, F, D, P, and S. So those central labels on the terms tell you the total angular momentum of the orbitals of the electron's orbits. So it has nothing to do with the spin yet. We're going to add that component in a second. So you can read this little chemist toolkit here. remind yourself about vectors. And then let's do another one that's a little more complicated. So if we have this system in self-test 8D.3, we have a D2P1. And so that means we have 3 electrons, and now their 3 orbital angular momentums can align in many different ways. So the way that you do this problem is that you couple 2 of them together, and then you couple the third one to your 2 couples. So we'd start out by, let's couple these 2. It's not going to matter which ones we couple first. We'll couple the 2 Ds first. So if we start with these 2, then L is going to be 2 plus 2, because each D is a 2, all the way down to 2 minus 2. So we're going to get a 4, a 3, a 2, a 1, and a 0, which is exactly what we just coupled in the last one. But now we're going to say, once these 2 electrons are coupled, now that third electron in a p orbital can also align in different ways. And so the overall L is going to be each of these guys coupled to this p electron. So it's going to, we'll start with this one. It's going to be 4 plus 1 all the way down to 4 minus 1. So that will give us a 5. And this is 3, 4, and 3. And now we have to couple the 3. So we're also going to have 3 plus 1 down to 3 minus 1. So we're going to have another 4 and a 2. When we couple the 2, we're going to have 2 plus 1 down to 2 minus 1. So this is going to be 3, 2, 1. When we couple the 1, we go couple it up here. So it's going to be a 2, a 1, and a 0. And the last one is the 0. So if we have a 0 plus 1 all the way down to 0 minus 1, absolute value, it's just going to give us a 1. So that means we have all of these terms. So this gives us a F term, a G term, and an H term. This gives us a G, oops. This should have also had a 3 in there, minus down to this one. So it's going to give us a G, an F, and a D. This is going to give us an F, a D, and a P. This is going to give us a D, a P, and an S. And this is going to give us a P. So that means we have an H from this guy. We have 2 Gs. We have 1, 2, 3 Fs. So these are different ways they could couple. We're going to have 1, 2, 3 Ds, 3 Ps, and an S, which is the same answer that they got. So a little more challenging just to think about coupling 2 first and then the third, but the rules are exactly the same. Once you couple 2, then these each become L1, and the last electron would be L2. So these are going to be different energies because depending on the orbital angular momentum, the system is going to have a different energy. So now we're going to think about how you can couple the spins together. So the spin angular momentum quantum number S is obtained in the same way. So you have the same kind of rules. So right here, it's exactly the same equation. So the total spin contribution to the angular momentum is going to be the two spins aligned together, the two spins aligned anti to each other. But then we're going to have to think about the fact that not all of them are allowed. So if we had, for example, a helium atom with 2 electrons, so that's going to be a 2s2. If we look at the possible spins, we have 2 electrons, and they can either be aligned or anti-parallel or parallel. But because they're in the same orbital, you can't have this situation. They have to be paired up. And so the only thing that's going to be allowed is the spin 0, where they're paired. So total spin of 0. So even though you'd use this equation and you'd say spin can equal 1/2 plus 1/2 down to 1/2 minus 1/2 equals 1 or 0. This one is not allowed because that's saying the two spins are parallel, and if they're in the same orbital, that can't be true. So when we look at putting together these term symbols, these symbols that label where transitions start and finish, we have to think about what we already know from Hund's rule and Pauli's exclusion principle. So let's see. Okay, so self-test 8D4. This says consider a configuration which is a 2p3. What's the highest multiplicity of a term corresponding to this configuration? So we haven't defined multiplicity, and I'll do that as I work this problem. So just like with orbital angular momentum, we can pair 2 spins and then pair that paired spin to the 3rd electron. So each electron always has the same spin. You don't have things like you do with orbitals where you have different angular momentum. So that means spin 1 and 2 and so you're going to have 1 down to 0. Then you have to pair that with the other electron. So now you start with that one and add it to S3, and you end up with 1 plus 1/2 down to 1 minus 1/2. So those are the only two when you start with this one. And then 0 plus 1/2 just gives you another 1/2. And so the largest spin would be this one, where they're all in the same orientation. So that would be what Hund's rule would say is the lowest energy. All 3 electrons are in the separate orbitals and they're all aligned. And so with the S of 3, the multiplicity is equal to 2 times S plus 1. So that would equal 2 times 3/2, which is 3, plus 1. So the state with the highest multiplicity is a quartet, has multiplicity of 4. So once we know about how the orbital angular momentums are paired, then we can think about how the spins are paired. Then we want to think about how they can pair with each other. So you can have orbital angular momentum pairing in the same direction or opposite, which gives you either greater or smaller angular momentum. The spins can pair or can be anti to each other or parallel. And so that also changes the energy of the state. But it changes the energy of the state also in terms of how those 2 types of angular momentums pair. So this last equation on the bottom says the total J, the total angular momentum quantum number for that atom, is a result of how the orbital angular momentum pairs to the spin. So this is exactly the same equation, You add them all the way down to the absolute value of the difference of the two. And so now we are going to get complete term symbols from a configuration. So we'll put together a complete set of numbers. Maybe I have room to do it on here. And this is for a configuration 4P1 3D1. And so what we're really thinking about is when you say something has an electron configuration of a port 4P1 3D1, you've thought of that in the past as that's an energy level. You could make a transition to or from that level. But this process of looking at how the angular momentums pair show you that that's actually split. There's more than one energy level within this based on the fact that the angular momentums can pair in different ways. So let's look at how we can pair them. Okay, so first let's figure out what our L values are. So we have L1 equals 1, L2 equals 2. So our total L can be 1 plus 2, 1 plus 2 minus 1, all the way down to 1, or yeah, 1 minus 2 absolute value. So it can be 3, 2, and 1. And the spin quantum number, each electron always has 1/2. So it can be plus, and it can be minus, so it can be 1, or it can be 0. And now when we couple those together, I need to grab another blank sheet of paper. Okay, so now when we couple these together, it's the same rules as we used here. To get the total J, we couple together this guy with this guy with this. So let me write something else. So this is an S. It should also be a 1 here. So we have a term S, a term P, a term D, and a term F. And now we're going to look at how those terms can have different total angular momentum based on how it pairs with the spin angular momentum. So when we look at L equals 0, S term, then it can couple with this, or it can couple with this. So our J can equal 0 plus 1, and that's it, because you go down by 1, so it can equal 1, or it can equal 0. So the S terms can have a J of 1 or 0. So let's write out what those S terms look like. So they're S terms. J goes here, so oops. J goes here, and this is a result of, yes, so this is a result of L equals 0, S equals 1, and so that means the total angular momentum is 1, and the multiplicity, which is the superscript, is 2s plus 1. This had a spin of 1, so that means this is a triplet. This had a spin of 0, and it has total angular momentum of 0, and it has, if that is 0, it's a singlet. So it's over here. It was when I coupled it with S equals 0, so that gives me 2 times 0 plus 1. So that's the coupling for the S terms. Then for the P terms, we'll couple it to each. So we will have so for each of the P terms, they can couple in different ways. So it can couple with this spin of 1. So I can couple L equals 1 and S equals 1. And when I do that, I get 1 plus 1. And then, so I get 2, 1, and 0. And then when I couple L equals 1 with S equals 0, I get a J of 1 plus 0, which is just 1. So, yes. So that means my P terms, I have a few of them. So when I look at the P terms I get here, so here are my S terms. My P terms that I get here would be P2, and I'm coupling with an S of 1. So that means 2 times S plus 1 is the triplet. And then I'll have a P1 that's a triplet and a P0 that's a triplet, because the J is the subscript for the total angular momentum. And then this will also be a P term, but it'll be a singlet because I coupled with S equals 0. So 2 times 0 plus 1, and the total angular momentum is 1. So those are my P terms. And what do I have left? I still have D's and F's. So my D's, D terms. So first I'll couple it with, S equals 1. So then J equals 2 plus 1, 2 and 1. So 2 plus 1, 2 plus 1 minus 1, all the way down to 2 minus 1 absolute value. So my J terms are going to be 3, 2, and 1. And when I look at those terms, I was coupling with an S of 1. So my D terms will be D, 3, 3, D, 2, 3, D, 1, 3. Now when I couple with L equals 0, or S equals 0, so now I'm going to couple L equals 2, so it's still a D term with S equals 0. J is going to equal 2 plus 0, 2. So the only term I get for this one will be a D term, which has total angular momentum of 2, and it's a singlet because S equals 0, 2 times 0 plus 1 gives 1. So I have 4 D terms. One left are F terms. So F terms are when L equals 0 or L equals 3. We still have to couple it to the 2 same S values. So when L equals 3, we have F terms. We'll start by coupling to S equals 1. So J will equal 4 plus 1, 3. And that's it for, yeah, because 4 minus 1 is a 3. So I only have 2 D terms. I feel like I must have done something wrong on this one. So, well, that's what I did wrong. I don't know why I said that was a 4. I'm sorry. So L is 3, S is 1. So you get 4. And then 3 plus 1 gives you 4. 3 minus 1 gives you 2. So you'll have 4, 3, and 2. So our terms for this one will be F4, and it will be a triplet. an F3, which is a triplet, and F2, which is a triplet. My very last one is also an F term because L equals 3, but we're going to couple it to S equals 0. So the only value we have is a 3. So it's an F term with total angular momentum of 3, and it's a singlet. And let's make sure all of those match. Yeah, it shows them in a different way. So you have an F3, 1, and then we have F that are triplets that are 4, 3, 2. Yeah, so we have all of the same terms, so you can compare my answers to their answers. So the important thing with this is that we're looking at saying that an electron configuration that we would have thought of as being one energy level is actually split. You have fine structure based on how the angular momentum is coupled. So that will influence how many peaks you see on your atomic structure. So the book then talks a little bit about the rules for what's lowest in energy. It's kind of counterintuitive. The highest J value has the lowest energy. Their argument is that if it has a high J value, the angular momentums are coupled together. And so it's actually the L values. So you're talking about the electrons orbiting. And if they're going in the same direction, they're not going to be running into each other. So that's lower energy. The other rule they give is that for atoms with shells that are less than half full, the level with the lowest total J lies lowest in energy. But for atoms with shells that are more than half full, the level with the highest J is lowest in energy. So you can do the self-test on page 384, and then it's easy to use that rule to figure out that it's the F3 triplet state that's the ground state for that particular system that we just looked at. Because it's, because it's the same system that we just looked at, a P and a D coupling together. So the very last thing your book talks about is what are the selection rules for atoms other than hydrogen. So delta S has to be 0 because the spin quantum number shouldn't change in a transition, but the orbital quantum number or angular momentum should change. As we said, the photon carries away 1 unit of angular momentum. So you have to take away 1 or add 1, depending on if the photon's absorbed or not, or emitted. So those selection rules are similar in nature, but they're slightly more complicated because of the electrons coupling with spin and orbital angular momentum. So when you only have 1 electron in the hydrogen atom, it's a simple rule. You have to change angular momentum by 1. Here you have a few more things you have to consider. And spectroscopy is a whole another field. If you actually wanted to take a course where you would see where this comes from quantum mechanics, it would be a much higher level course because you have to do time-dependent quantum mechanics, which is just a whole nother ballgame. So you're just gonna have to trust those rules are valid.